Hi, everybody. We're going to go through the major topics for this upcoming test. Please make sure that you do look over the layers of the atmosphere. What I'm going to cover in this video are weather versus climate, albedo, ozone, greenhouse effect, and then some laws that relate to air pollution as well as anthropogenic and natural ozone creation and destruction. First, a couple of basics. Weather versus climate. Whenever you think about the word weather, what you want to imagine saying is, what's going on right now or this week or this month? You know, the weather in May is often rainy. When you talk about climate, you really want to be talking about the largest data set you can. Ideally, 100+ years starts to get you towards climate. What is happening to the overall planet over a very long period of time? What are humans doing that are influencing this trend? Albedo. Albedo is a measure of reflectivity. Overall, Earth's albedo is lowering. In other words, it means that the planet overall is becoming darker. Why is this a concern? Because as we talk about ultraviolet radiation, both in relationship to the ozone layer as well as to the greenhouse effect, how much solar radiation is going to be absorbed versus reflected on Earth really matters. Things like ice and ice caps have a high albedo. Unfortunately, land that has a high albedo, in other words, natural surfaces, are diminishing as our population becomes larger and as our cities become more sprawling. i.e., we are taking high albedo surfaces and turning them into low albedo surfaces. When we do that, more of the solar radiation is being absorbed into the land, thus the troposphere is warming. Here's simply another way to look at this if we just look at it in relationship to reflectivity. When you have a surface without snow and ice, look at the yellow UV. That's what's getting absorbed and that's what's getting reflected. Now, if we have a white surface like snow, this is what's getting reflected and this is what's getting absorbed. So the troposphere is fundamentally cooler when we have a white surface. In other words, a lot of reflectivity, and fundamentally warmer when we don't have white surfaces, either green and brown natural surfaces or black and brown man-made structures, cities, housing developments, businesses, industry, all of that sort of stuff. So let's take a look at what's happening to all of the solar radiation. We're going to divide this into two sections. The left section, this is all of the solar radiation coming in, 100%. You can see that some of it is reflected in the atmosphere and some of it is reflected by the surface of Earth. Some of it is going to end up being absorbed inside the atmosphere, but 47% of it is going to be absorbed by land. Now we talk about the right-hand side. Once it's absorbed by land, this is UV radiation mostly. It's going to actually end up being re-reflected usually as infrared radiation. The infrared radiation has a longer wavelength and it's going to relate to the greenhouse effect when we get there. But this is what is happening to the long wave radiation. So this 47%, this is how it gets chunked out. Let me just let you take a look at that for a moment. If you need more time, you can pause the video now to take some notes on both the incoming radiation as a whole, as well as the re-radiated radiation. Please keep in mind, global warming is 100% necessary. If we didn't have any global warming, then the planet would be so cold that things like farming wouldn't really be a reasonable way for humans to get food. In other words, if we had no global warming, really complex human-like life would probably not have been capable of forming the way that it did on the Earth's surface. What we're concerned with in relationship to global warming is the anthropogenic warming. So when we talk about the greenhouse effect is an awesome thing. But when we add in these anthropogenic items, that's when basically the greenhouse effect starts to roll into global warming or global climate change, and that's when we as humans end up having a concern or an issue. There are natural and man-made sources of greenhouse gases. I'm just going to let you take a moment to scan down these. These ones here are natural sources. If you need more time, you can pause the video. Here are human or anthropogenic sources of greenhouse gases. Again, if you need a moment, you can pause the video. When we talk about these pollutants that are going out into the air, there actually are two types of pollutants. They're going to be primary and secondary. I actually would prefer to look at these on the next photograph, which is a picture of the natural and anthropogenic sources. So if you want to take a longer look at this slide about what primary and secondary are, you can pause the video and just scan through that. Okay, so here are primary. Now, primary can be either natural, like from a volcano, or they can be anthropogenic from industry or agriculture or transportation. These are all primary pollutants. These are things that go from an object into the atmosphere. Now, to get to be secondary, oftentimes they're going to actually mix with something, oftentimes water. Now, the good thing and the bad thing about this is that many primary pollutants are what we call water soluble. In other words, they are able to mix with water and exit the atmosphere in a reasonably short period of time. Now, when they do, they can be damaging. So, for example, the sulfur dioxide, when it mixes with water, becomes H3SO4 or sulfuric acid, hence acid rain. So, it's not exactly that primary pollutants are worse or better than secondary pollutants. It's just kind of a transition that you want to know is happening in the atmosphere, and then you want to know that the chemical reactions are changing, and that when these things do come down to earth, they can cause concerns. They can acidify oceans, they can damage plants, they can, if they're these salts, they can change the pH of the land and things like that in a way that is a concern for human health. The one that we're going to focus on in a moment is O3 or ozone. Where does it belong? Where is it supposed to be created and destroyed? Where is it anthropogenically being destroyed? And what happens when this O3 comes down to our tropospheric level? What does that do to human health? Ozone. It's supposed to be naturally created and destroyed. And if you go on to Google Classroom, there are two videos that will show you exactly how it is naturally created and destroyed. This slide is on natural creation and destruction. We have single highly charged oxygen that meet up with breathable or diatomic oxygen. The reason that they're able to combine is that UV radiation has come in and has given these particles extra energy, which makes them highly energetic, which makes them able to hook up in this unusual O3 structure. This is a much stronger structure for oxygen. Oxygen loves to just find one other of its kind and come together, but it's not very good at blocking solar radiation. Ozone is really good at blocking solar radiation. So essentially, solar radiation, the arrows here, take these two items, join them together to form the weaker bond of O3. But the solar radiation also does the exact opposite. When it comes down and strikes these ozone particles, the ozone absorbs that radiation, saving the organisms on the surface of Earth from potential DNA or cataract damage, and they they actually split them out into breathable oxygen and ozone. But don't worry, these two parts are going to go back and create more ozone. So these two are in balance in the atmosphere because this is the way that it's naturally supposed to break apart and come back together. Let's look at the players for anthropogenic. They should be familiar from the last slide. We have the single oxygen, we have the diatomic or breathable oxygen, we also have ozone. And then we have the anthropogenic molecule CFCs. There's not exactly one chemical formula for this. Basically, what we're going to focus on is one of these molecules. This can be chlorine, fluorine, bromine, and sometimes even nitrogen. These items in the ozone layer are capable of destroying ozone anthropogenically. Let's look at that process. I realize that this is a little bit blurry, but there is a video, the 5-minute video, that will go through this entire process in the first 3 minutes. So if you would like a review past this on Google Classroom, there's a wonderful video. The first 3 minutes will go through exactly what I'm going to do, except in animated form. Here are the players. Ozone, the awesome molecule for blocking solar radiation. CFCs, a byproduct of manufacturing. Solar radiation comes in, and it's capable of breaking the bonds. So it frees this chlorine from its CFC brethren. The chlorine's really unhappy. Let me actually scan forward for one moment to show you a periodic table. Fluorine, chlorine, and bromine are all poisonous gases in their elemental form. But when they hook up with other elements, they can form things like air conditioning, refrigerants, they can accelerate gases for things like fire extinguishers. But the problem is that when those items get crushed and those gases inside that are doing the cooling and the accelerating escape, these are the sources of anthropogenic destruction in the upper atmosphere. Remember, whenever they're in a column like this, they're going to share characteristics. So we're going to focus on it being chlorine. This chlorine is desperate for one additional electron. And remember, I told you that the ozone bond isn't all that strong. So the chlorine comes along, breaks the bond, and forms two new molecules, the oxygen, breathable oxygen, and a thing called chlorine monoxide. Now, the problem is this is also a pretty weak bond. Oxygen doesn't love being paired up with chlorine. So as soon as that oxygen finds a free oxygen, it ditches the chlorine, gets remarried to another oxygen so that they can be best friends, and the chlorine goes out to find a new partner. The problem is, remember, this and these single oxygens, they're not good at blocking solar radiation. They're not designed to do that. That's what ozone's designed for. So when this bond happens and this bond happens, the chlorine is destroying the useful molecule of ozone in the stratosphere, in the ozone layer, and it's creating useless products that are not capable of keeping humans and other organisms safe from UV radiation. So this is a picture that just shows you where ozone's supposed to be. There is supposed to be a teeny tiny amount down here, but if we get any more than a teeny tiny amount, it's really poisonous to humans. Then we have this big fat layer here. This is the ozone layer, and then it trickles off in the stratosphere. So basically, from the tropopause up to about halfway through the stratosphere is where the ozone layer is the thickest. And it does move around seasonally, so this is just kind of an approximate. So again, even tiny amounts of ozone breathed in daily at the tropospheric level can be really harmful. It can cause all kinds of breathing and other issues. There's a video under here. This is the first one. The one that shows you about natural and anthropogenic ozone creation and destruction. Now, here's a look at what happens. This is what's supposed to be going on. We're supposed to have a lot of this ozone up here in the ozone layer. But this is what's actually going on over many parts of the Earth. The ozone layer is thinning due to anthropogenic damage. And so more solar radiation is reaching Earth's surface. Look at the number of arrows here. Look at the number of hours there are supposed to be. This corrupts DNA and can cause cataracts. This is a more normal amount of UV, generally UVA and B, that's supposed to be coming to Earth's surface. This allows more UVB than is appropriate to keep humans and other organisms healthy. Here are just a list of some of these man-made pollutants. Here are your CFCs, your halons, and then remember I told you bromine, this is methyl bromide. So you have aerosols, refrigerants, air conditioning, fire extinguishers and other extinguishers, as well as agricultural pesticides. All of them have elements in it that can lead to the destruction of the ozone layer. This is another video. I would at this point maybe pause this video and watch this one. This one will go over the 3 things needed to destroy ozone over Antarctica, as well as what is the outcome of the ozone hole over Antarctica. You can always come back to this video when you've watched it. So if you've watched the video, this is a summary of what is said. Firstly, you need lots of chlorine and bromine. Second, you need really cold temperatures. And then third, remember, Antarctica is in the southern hemisphere. So August and September are much more like our March or April. It's right at the beginning of spring. And that's why at the end of August, the beginning of September, that's when the sun is actually rising in Antarctica, because they have the exact opposite seasons because they're in the southern hemisphere. So the solar radiation shows up in August and September, thus beginning the destruction that will culminate about midsummer. Now, sometimes we actually end up moving ozone out of the ozone layer and down to the troposphere. And we do this when we have too many natural mixed with anthropogenic chemicals. You can actually rip the tropopause. And remember, gases go from areas of high concentration to areas of low concentration. And so this ozone-rich air will go from the high concentration, where it belongs in the ozone layer, down to the troposphere. And this is where it can cause serious issues. Remember, stratosphere, good ozone. Troposphere, bad ozone. There's no way for that ozone to block solar radiation in the troposphere. All it can do is cause humans to have health effects. Greenhouse effect. The greenhouse effect is natural. It's supposed to be there, and it's supposed to moderate the temperatures on Earth. So let's take a look at some greenhouse gases that are supposed to be out there, that are supposed to be trapping solar radiation near Earth's surface, giving us a good climate that doesn't swing too much, even though it feels like it does from winter to summer. Overall, the actual global temperatures are very moderated, so that humans can essentially live on the surface of Earth 365 days a year, and that we can do a lot of farming in a lot of places for enough time to grow up fruits and vegetables that support our population. I'll just let you take a look at this. The largest anthropogenic one is carbon dioxide, but interestingly, the largest greenhouse gas period is water vapor. Now, this is radiation. The 2 radiations we're going to talk about are going to be ultraviolet and infrared. Ultraviolet is the radiation that comes in from the sun that partially passes through the ozone layer. It's then going to be absorbed by Earth's surface, depending on whether that surface has a high or a low albedo. When it is re-radiated, it is mostly re-radiated as infrared. And what happens to that infrared, if most of it passes out back into outer space, that's the natural greenhouse effect. When we start to get into global climate change, we'll talk about how some of those gases from the last slide are trapping more solar radiation at Earth's surface. Left-hand side is shortwave. Infrared's the most important. Right-hand side is long wave. We talk the most about ultraviolet because that is what is capable of passing through our Earth's atmosphere. So this is what's supposed to happen, right? This shortwave UV comes down, number one. Most of it is supposed to bounce back out. It's supposed to strike a white or a high albedo surface, and most of it is supposed to be radiated. Only a little bit is supposed to bounce. You see this number 3? This bounce is the greenhouse effect. It's what's infrared radiation that's warming up Earth's surface. The problem is this isn't what's happening anymore because of man-made items in the atmosphere. What's actually happening is more like this. Here we have our solar radiation that's coming in here. It's striking Earth's surface and it's warming Earth's surface, but only a little bit is able to escape out past all of those greenhouse gases. What's happening is that most of it is bouncing around and hitting Earth's surface, warming it up more. Keep this in mind when we get to global climate change because the greenhouse effect plays directly into global climate change. So let's look at those two together. Natural greenhouse effect. Solar radiation comes in, lots of solar radiation escapes, only a little bit bounces around in the troposphere. Now, unfortunately, we have basically the same amount of solar radiation, but look how much more of it is bouncing around and how little of it is escaping out into space. This is where the greenhouse effect meets with global climate change. If you'd like a review of that in words, pause the video now and you can scan through this. Okay, there are some laws that influence the atmosphere. Some of them are good news, some of them are potentially good news, and some of them are not perfect. Annual emissions. China and the United States are the two top emitters. China emits the most CO2, but the United States emits the most per capita. So in other words, Americans use the most CO2 per person, but China puts out the most CO2 overall. This will end up being really important when we look at global climate change. Okay, Montreal Protocol. This is the super good news. It was passed in 1987 and it was wildly successful. Essentially, when we stopped putting chlorofluorocarbons, bromines, and halons out into the atmosphere, the ozone layer naturally repaired itself. People basically said, we can't have a hole in our ozone. We need you, companies, you legislators, and you consumers to all stop buying products that have this in there, and people actually did. It was ratified by basically everybody in the entire world, almost everybody in the entire world, and it is helping to allow Antarctica's ozone layer and really the entire world's ozone layer to thicken up and recover, hopefully by 2050 where we live, and by 2065 the Antarctic hole will be at pre-1980 levels. Here is a picture of who ratified the Montreal Protocol. If you notice, pretty much everything's blue. This was a worldwide effort. Very few countries did not sign. Now, this one is a domestic act. There are two Clean Air Acts, one in 1970 and one in 1990. These were moderately successful. The idea was mostly to try to reduce things like mercury and lead. So this is where if you ever go to the gas station, you have unleaded gasoline. It was when things like sulfur dioxide, nitrogen dioxide, mercury, and lead emissions were all they worked to limit them in any kind of combustion. This would be in electricity production or in driving cars and doing transportation. Reasonably successful. The 1991 essentially put in more regulations and helped to firm up the 1981. If you'd like to read this some more, you can pause it. Kyoto Protocol. Sadly, this was in 1997 and it wasn't very successful. Let me show you the world who signed and who didn't, and you'll basically figure it out why it was not terribly successful. Kyoto was working to try to reduce anything that relates to global climate change. So this would be things like methane and carbon dioxide emissions. Notice who didn't sign. The United States didn't, Canada didn't, Russia didn't, Mongolia, most of the Middle East, and large chunks of Africa. When you don't have most of these players on board, it just basically means that it has to be a global effort. And so if the largest polluter per capita, the United States, doesn't sign, that's an issue. Even China signed because China was very concerned over the fact that their air pollution is so bad. The Chinese citizens wanted to make a global push to both clean up their air as well as to hopefully reduce the effects of global climate change. Now, here's the better news. This is the Paris Agreement. I have an older map up here in a moment. Actually, let me just say, if you'd like to look at this screen, pause it now, because I'd rather talk about this over the map. So I'll just give you a moment to decide if you're going to pause. So the idea of the Paris Agreement was to keep global temperatures from rising more than 2 degrees above industrial levels. Now, the good news is that the United States has actually gone back to joining. So going back to be a joined signed partner. President Trump withdrew the United States. Very recently, President Biden has put us back in. So this black is now a dark green. And you can see that many more countries signed up for Paris, because we can see the writing on the wall. If we don't work to mitigate global climate change, don't work to mitigate these anthropogenic air pollutants like carbon dioxide, methane, we're going to end up with a planet that's not going to support humans in what we would consider a reasonable lifestyle. Long-term effects of not addressing air pollution. Rising sea levels, because the Earth will get warmer. Melting glaciers, in other words, a lowering of the albedo, i.e. more of that solar radiation that comes in as UV will bounce around as infrared and will make the troposphere warmer. Changing weather patterns, more severe floods, more severe droughts. Basically, whatever's the worst weather will happen more often. And then a limiting of biodiversity or an extinction of species. Remember, there are some videos inside here, and there's a study guide up online. Good luck on the test next week.